So it's probably time to introduce some algebraic notations. So what do we see here? Well, let me just rewrite this over here. F of x, y is actually equal to x cosine 2 minus y sine 2, comma, x sine 2 plus y cosine 2. Alright, now at this point I would like to have some notations in place, and those notations are coming from linear algebra. Basically, if you look algebraically at functions u and v, and those functions as functions of x and y are linear, that means algebraically you can write that as a constant plus another constant, let me call it m11 multiplied by x, plus yet another constant m12 multiplied by y. And any linear function should look like this, if that is a linear function of x and y. And again, any linear function v will be in the form c2 plus m21 times x plus m22 times y. And for our calculus course, from calculus point of view, these constants have different importance, because these two, the constant c's, they represent just a constant that has no meaning towards the dependence of u on x, or at least minimal meaning. The meaning of m11 is the rate of change, and that's the key concept in calculus. m11 represents the rate of change of u with respect to x. m12 represents the rate of change of u with respect to y. m21 rate of change of v with respect to x, v with respect to y. So these four numbers are going to be of central main importance for the whole calculus course for that reason. They represent the rate of change of dependent variables upon independent variables. And that's why I will put those together, and when I put those together, these four numbers will make a matrix. Let's call it M. So that matrix is made of numbers M11, M12, M21, and M22. And let's quickly figure out what these matrices are in all those cases. So in this case, the matrix is made of cosine of 2, negative sine of 2, sine of 2, right? The rate of change with respect to x, with the rate of change with respect to y is cosine of 2. All right. That's the matrix that determines geometrically geometric transformation being rotation by the angle of 2 radians. Now, what if rotation happened to be by a different angle, let's say angle alpha? What would be the matrix? Well, it will be cosine of alpha, sine of alpha minus sine of alpha, cosine of alpha. Very easy. You can track that appearance of number 2 through the whole computation and see that it shows up exactly as angle in those sine or cosine functions. So in general, geometric rotation by the angle alpha is represented by a matrix made by those cosine sines. Now, what about this example? Circulation. So what's the matrix representing this phenomenon algebraically? The rate of change of u with respect to x is 0. The rate of change of u with respect to y is -1. The rate of change of v with respect to x is 1, the rate of change of v with respect to y is 0. So that's the matrix, and that needs to be multiplied by omega if there is a non-unit angular speed involved. And, well, what do you think should be the rule of multiplying a matrix by a number? Well, the very intuitive rule, very simple rule, is that you multiply each number by that omega. So you get 0 minus omega, omega, and 0. So that's the matrix representing circulation in physics with angular velocity omega. Alright, what about constant flow? What is the matrix that works here? The matrix is rate of change of u with respect to x, that's 0, with respect to y, 0, 0, 0. 0 matrix. It's really a constant phenomenon. There is no rate of change involved. In some sense, the derivative is 0, but we will talk about it later. What's the matrix for this function that geometrically represents translation? Well, that is rate of change of u with respect to x is 1, with respect to y is 0, the rate of change of v with respect to y is 1, but the rate with respect to x is 0. So that's the matrix for translation. Alright, so now we have all these examples described algebraically using matrices, and our next attempt would be to look at matrices from algebraic standpoint and try to understand all possible matrices. So algebraically, matrix is going to be for us a way to represent linear function from a plane to a plane. So we will have to understand everything about all the matrices, and hopefully we will relate what we understand to those simple examples. And if we understand something simple about those matrices and about linear transformations, about linear functions, we will hopefully translate that understanding to physics and geometry, saying that certain flows are very simple, those are linear, and you should consider them as the simplest flows ever. And also, certain geometric transformations are very simple, they are linear. And all that will come from linear algebra. Alright, that's a good point to stop.